So as an example of a system with a wedge, we're now going to solve this system here, where the wedge is really a right angle region. It's the first quadrant. And we've got particularly simple boundary conditions. Temperature T0 along here and temperature T1 along the y-axis. So the simplest way to do this is to use the formula, which we can only use if these are constant. T of xy is equal to actually, before we do this, it's slightly easier just to illustrate this approach. If we say, well, this is equivalent to if we introduce a new variable u, which is equal to t minus t naught, then obviously taking the Laplace equation of that, then the del squared u is also equal to 0, since t naught is a constant. And this is equivalent to solving the problem u equals t1 minus t naught along here and u equals 0 along here. So it tends to be easier if we've got one side is equal to 0. Anyway, just to illustrate, in this particular case it doesn't make that much difference, but for more complicated problems it's good to do this sort of thing. Okay, anyway, just to sort of illustrate it, we'll do that. So now we're solving the problem for u. So u, because it's a wedge type situation, should equal a times arg z plus b. And we just have to fill in, consider the two cases. So the case along here, we've got arg z along here, arg z equals 0, and we've got u equals 0. So therefore, well, u equals 0, arg z equals 0 implies that b equals 0. And then along here, we have u equals t1 minus t0, and arg z along here is pi by 2. So that gives us that t1 minus t0 is equal to a times pi by 2, which in other words, a is equal to 2 t1 minus t0 over pi. So that means we've got as our u is equal to t1 minus t0 is 2 over pi arg x plus pi y. And to get back t is just this plus t0. So we end up with the solution t of xy is equal to t0 plus 2t1 minus t0 over pi. So this is the quickest way of solving this problem. But just to illustrate the idea of conformal mapping, I'm now going to solve the same problem using the conformal mapping approach. Okay, so what we want to do now is transform this into the w plane, which the upper half of the w plane. So we've got this situation here. This is now the w plane. So to do that, the transformation from here to here is just w equals z squared. Okay. And then the boundary conditions in the w plane are then just transformed are transformed. Basically, this gets transformed to here, and the t1 gets transformed to here. I could, of course, also change variables to u and do the same thing, but I'll just keep it like this to keep things simple. I mean, in the end, it doesn't make much difference if you use u here, because, okay, this formula is so simple to use anyway. So anyway, now we've got this situation. and we can write down the solution to this. This is very similar to what we've done earlier. We've got in the W plane, we have t, I'll write it as t tilde. Okay, so now we're solving t tilde, del squared t tilde in the W plane. Is equal to this value here, t0, plus 1 over pi. x1 is 0, so we just end up with this minus this, so it's this minus this, so it's t1 minus t2 times arg of w. Okay, so I said x1. This should be u1 now. So we've got everything in terms of x is now u. So we end up with that. So to get the final answer, we need to convert this. We need to rewrite this in terms of x and y. Now in this particular case, w is equal to z squared. But the argument of z to the power of anything is just that power times arg z. So we can move this 2 to outside. And then I should now writing things in terms of x and y. I can actually go back and write this as t in terms of x and y. And then this, you can see, is just the same as this.